All right, so we are on Module 13. We're going to start today with the review questions, and then we'll hop over to the practice problems. All right, so let's start with number 1. It says, in a chemical reaction, where is the potential energy? Where is the kinetic energy? So really, we want to know where are these two types of energy found in your chemical reaction. So if you remember, the potential energy is stored in the bonds of the molecules. So if I have a chemical reaction right here, and these are my reactants and these are my products, all that potential energy is going to be stored in those bonds, because when we break them down, that's where we're getting that potential energy. Okay, so then where's the kinetic energy found? Typically it's found in motion. So if you think about it that way, you should remember that the kinetic energy is actually in the heat. It's either the heat absorbed or the heat released during that reaction. So whether it's absorbed over here or whether it's released as heat over here, hot and cold, that's the kinetic energy. All right, number 2. If a chemical reaction has a positive delta H or positive enthalpy, will the beaker that contains the reaction feel hot or cold once the reaction is finished? So what they're really asking you is, if you have a delta H that is positive, so if you get a positive number when you crunch that out for enthalpy, or a change in energy, a positive change in energy, which side is that going to belong to? So if you remember, we had our sign right here, and we know that any delta H that's negative is going to go here, and any delta H that's positive is going to go over here. So if I have a positive, we know that it's going to go on this side. It's going to be one of the reactants. And so that means it's endothermic, okay? And they ask, is it going to be hot or cold? We know it's going to be cold, because whenever it's endothermic, endo in, it pulls the heat in from the surroundings. So if it's pulling the heat in, that means the surroundings are actually getting colder, as opposed to the exothermic, exo out, heat out, putting heat out into the surroundings, so it's actually getting hotter. So cold, hot, positive, negative, endo, exo, okay? All right, let's look at number 3. It says, why is Hess's law a more exact way of determining the enthalpy than the technique that uses bond energies? So we're really looking at the difference between bond energies, which means we're breaking it down into the Lewis structures, versus using Hess's law, which is our products minus our reactants in our table. So Hess's law is more exact because it takes into account the phases. So if I have gas, liquid, solid, stuff like that, Hess's law is more precise, it's more exact. The bond energies don't have phases, so it's not quite as accurate. Number 4, what is a state function? Give 2 examples. So a state function, if you remember when we were talking about this during the lesson, I gave you the example of graduation. So if you're a homeschooler versus a public school versus a private school, you're all taking different paths, but you're going to the same final destination, which is graduation. So we would say graduation is a state function. So a state function is basically just, it has a final value that isn't dependent on the path that's taken to get there. That's the definition of that. And it says give 2 examples. Well, you learned 2 different examples in this module, and the first one you used was enthalpy, and the last one was Gibbs free energy. So you could say delta H and delta G, okay? Those are 2 different state functions. All right, number 5. It says, which of the following substances, and then it lists them, will have a standard enthalpy of formation of 0. So they have NaOH, Na plus, O2 gas, Cl2 gas, H2L, okay? So the first one, that one is not one, because it's a molecule. So if you have any molecules, those are not one. This one, I'll put that up here, molecule. This one is an ion, we can tell because it's got a charge on it. So that also cannot be one, okay? Because remember, when we have delta H's of 0, it has to be just an element in its correct elemental form. So here we have O2 as a gas. That one is 1, okay? Because it is, oops, I forgot one right here too. I'll get to that one next. It's correct, it's a dihomonuclear atomic ion, and, sorry, not ion, atom, and it's in a gas form. So let's go to the next one. If you look at this one, this is close, but it's not quite correct because we have to have, the oxygen doesn't just exist by itself as an atom in nature. It always exists with another oxygen paired. So this would be the correct one. This is not correct, okay? And chlorine, again, this is just an element in its correct elemental form as a gas. And H2, this is not one because hydrogen is not a liquid. It is a gas, okay? So we would cross that out. So we only have these two, okay? So I think you're going to do something similar to that on a test. You just have to be able to identify which one is going to have a 0 for the elements. Okay, number 6. It says, which of the following diagrams indicates an endothermic reaction? What is the delta H of that? So then they give you two different diagrams, diagram 1 and diagram 2. Okay? And the basic one of diagram 1 goes like this, and diagram 2 goes like that. So it says, which one's endothermic? So really all you have to do is take your products over here, whatever this value is, minus whatever this value is. So for that first one, I had 70 minus 15, it's 55, and over here I had 90 minus, 60 minus 90. And that equals negative 30. So they asked, which one's endothermic? We want a positive answer. So this one is endothermic. And then it asked, what is the delta H? Well, this is the delta H. That's how we found it. So I would say 55 kilojoules. That's my delta H. Okay. You're going to have to be able to look at a couple diagrams for the test and be able to tell which one's which one's going where, and just be able to generally answer questions about them. All right, let's look at the next one. It says, number 7, draw an energy diagram for a reaction that has a large activation energy and a delta H of 0. So large activation energy, we want that really large hump. It takes a lot of energy to get that reaction going. And if we want our delta H to be 0, wherever we start, that's got to be our ending point value as well. So if I was sketching a graph, I would maybe start further down, give a large activation energy, and then I have to end at the same value that I started. Okay, so if I said that was 100, that would have to be 100. So this is the large activation energy. So anything that looks similar to that. Okay. Number 8 says, if you have two 50.0 kilogram blocks of copper, so they're both the same, and one is at a temperature of 50 degrees Celsius while the other is at a temperature of 25 degrees Celsius, which has more entropy. Remember, entropy means more disorder. Higher entropy equals higher disorder. So if I have one at 50 degrees Celsius and one at 25, roughly, remember, this is where our sign comes in right here. So we're dealing with temperature, so I know that the higher the temperature is entropy increases. So between these two, they ask which one has more entropy. I'm going to go with the higher temperature, okay? Anytime it's a gas, has more of something or higher temperature, that's going to be higher entropy. Number 9, when you study your brain neurons store information, this causes the brain to become more ordered. Why doesn't that fact contradict the second law of thermodynamics? So remember when we talked about this, when we look at the second law, we have to look in total, the whole universe, okay, the whole idea. So you can't just look at one thing and say, oh, my brain's getting more organized as I study, therefore it's wrong. It's getting more ordered instead of less. You have to look at all the things around it. So you could easily say, okay, even though my brain's becoming more ordered, what's becoming more disordered? Well, your body is burning calories as fuel, right, to be able to support your brain activity. And whenever you burn things, it's going to heat up the surrounding area. And we know as heat increases, just like this, entropy increases. So we could make we could look at everything around that situation that's happening and say, although one is becoming more ordered, there's other things becoming more disordered, therefore the second law of thermodynamics is not being broken. It's still being held up. And number 10, it says, if a chemical reaction is exothermic but has a negative delta S, what could you do to the temperature in order to make it possible to run the reaction? So real quick, the book doesn't really talk about this very well, I think. So we're going to go ahead, and if you remember, here's delta H minus T times delta S less than 0. So if this is true, it's less than 0, then it's spontaneous and it can run, okay? So they said, if a chemical reaction is exothermic but has a negative delta S, what can you do to the temperature? So let's just try a few things, okay? We're going to plug some numbers in here as an example, and we're only going to change the temperature to see what happens, okay? So I'm just going to stick in 50 here, and then for temperature I'm going to pick 25 times, and they said the delta S was negative. So I'm just going to pick a negative value, -2, okay? So right here, if I crunch all this, I'm going to end up with 100 on this side, okay? Now, let's increase this and decrease this. We want to see what happens as we change the temperature while everything else stays the same. So if I increase it to 50, let's say, then my outcome is going to be 150 over here, okay? So as I increase the temp, I also increased this whole side. So let's go ahead and decrease it now. We increased it from 25, let's decrease it to 10. So if I crunch this out, I'm going to end up with 70. So I can see here, this still wouldn't be true. 70 is less than 0. So I can see that I'm going to have to actually take my temp, and I'm going to have to keep lowering it. So let's do something quite a bit lower than 10. Let's pick -50. Oops. And let's see if we can get this to be less than 0, get it to be true. So if I lower the temperature this much, it's going to be equal to -50 over here. That is true. So the question really asked, what do you have to do to that temperature value to make it possible to run? Because remember, this has to be true in order to run the reaction. Well, we just had to lower it low enough. So we had to lower the temperature far enough to be able to make this reaction run. So you could solve for this and see exactly what it is. They didn't ask you to do that. So I just had to show and prove to lower it. You're going to have to do something like this on the test. So if you need to kind of go review this here, I think the extra practice problems might have one like that for a little bit more help. All right, so that's the end of the review questions, and let's move on to the practice problems.